Up to this point, we've discussed the geometric series, and we've talked about when it diverges and when it converges. We've talked about the nth term test. The nth term test suggests that if the individual terms don't approach zero, then your series is going to diverge. You have to be really careful, though, because there's a tendency for people who don't understand the nth term test very well to just start assuming, oh, okay, if the individual terms approach zero, then it's going to add up to equal a sum. And unfortunately, that's not always the case, okay? That works with the geometric series. It doesn't necessarily work with other series. In a very famous case in which a series with terms that approach zero diverges, a famous case is called the Harmonic Series, okay? Very, very famous. The Harmonic Series is the series from 1 to infinity or 0 to infinity, depending on how you set it up, of 1 over n. So you're going to get 1 over 1, plus 1 over 2, plus 1 over 3, plus 1 over 4, and so on. And on the surface, you think about that and you say, okay, this is going to extend out infinitely. The individual terms will approach 0. And again, if you don't really have a good understanding of series, you might think, hey, the individual terms go to 0, this is going to converge. And that's not true, okay? The nth term test just basically shows that it doesn't necessarily diverge, but you still have to find some other kind of test to try. So once you find out that the individual terms approach 0, the nth term test can't tell us that it diverges for sure, but it's not telling us it converges, okay? We have to find some other kind of series to compare it to. So you check and you see if it's geometric, and hopefully you can tell here you're not multiplying by the same value each time. It is not geometric, okay? Anyway, here's the deal on the harmonic, and this can be proved in lots of different ways. All right, so the idea here is to try to bound this. You should be able to show that there's a series that has terms that are smaller or equal to the terms in this series that diverges, okay? So if you've got a series with terms that are less than or equal to the terms in this series, and that series adds up to infinity, you know this term is also going to add up to infinity, okay? So the concept here is basically that we're going to look at, for example, okay, so I've got 1, I've got a half. 1/3 is a little bit bigger than 1/4. Okay, if you think about breaking a pie up into 4 pieces versus breaking it up into 3 pieces. So 1/4 is a little bit less than 1/3. Okay, and then this is still 1/4 here, right? So 1/4 plus 1/4 adds up to be 1/2. Okay, my series already has a 1/2, and of course my series already has a 1 before that. Okay, now if I jump out to 1/8, okay, all of these terms are greater than 1/8. Okay, so 1/8 is a little bit less than that. 1/8 is a little bit less than that. 1/8 is a little bit less than that. Okay, well, if you add up 1/8 plus 1/8 plus 1/8 plus 1/8, you get 4/8, which adds up to 1/2. Okay, and you can keep doing this. We can go out to the 16th term. Okay, 1/16 is smaller than all of these other terms. Okay, so if I replace that with a 1/16, and I replace this with a 1/16, and I keep replacing all of the terms with 1/16, which is smaller than all of these other terms, okay? If you add this up, I have a total of 1, 2, 3, 4, 5, 6, 7, 8. 8/16, which simplifies down to a half. Okay, I can do the same thing. The next 16 terms, I could replace all of those terms with 30 seconds. 16 30-seconds adds up to a half, and so on. Well, what I've shown here, not formal proof, but I think you can kind of see what's going on, is I can basically turn this into a series in which I get a half, plus a half, plus a half, plus a half, plus a half, and I can continue that out as far as I want. And because I can continue adding on a half as far as I want, this series diverges. Okay, the harmonic series is divergent. And by the way, lots of variations of the harmonic also are divergent. So for example, if I multiply this by 5, if I had 5 plus 5 halves plus 5/3 plus 5/4, that's going to be a divergent series, okay? It's a series that has terms that are bigger than a series that already diverges, okay? If I multiply it by 1/2, and I had 1/2 plus 1/4 plus 1/6 plus 1/8. Okay, I would just be taking a half of a divergent series. If something adds up to infinity, half of that still is going to add up to infinity. So any multiple of that, whether or not you're multiplying by a fraction or a whole number, is going to end up also diverging. Okay, at least if you're looking at whole number values. By the way, just a little bit more background here. What I've actually shown is that this series is bounded by a divergent series that has terms that are less than or equal to the terms of the original series. Okay, so in other words, if I can show, hey, there's a series in which all of the values are less than or equal to the values of this series, and that series diverges, then a series that has some terms that are bigger than these terms is going to have to diverge as well, because we're going to get something that's bigger than infinity when we add all those terms up. Okay, so that's the basic idea there. So anything that turns into the harmonic is going to be a divergent series. Okay, I want to show you one additional example, but I think I'm going to stop the camera and start it up again. So I'll be back in just a second.